Oh.
The other one?
Oh no. Yeah. 1, 2, 3. Seems to work. I can move it up a little. Just do the usual thing and just move it up.
This looks like it has enough back.
Yeah, it should work. Let's try.
Are you going to do it?
It seems to be fine. All right. Yeah.
All right, let's resume our discussion of generalized symmetries with Thomas.
All right, so let's continue our discussion of this abelian Higgs model with the charge Q scalar. And we discussed the Coulomb phase that you get for positive masses. Now I'm going to discuss the Higgs phase for negative m squared. So this model with negative m squared is basically the Landau-Ginzburg description of a superconductor. Yeah. 4D, always. So if you think of H as describing some condensate with electric charge Q, you can think of this as a 3 plus 1 dimensional superconductor. All right, so if m is negative, then H gets a VEV. And since H has charge ZQE, the U1 gauge symmetry is Higgs to its ZQE subgroup. In sloppy parlance, we say it's spontaneously broken to its ZQ subgroup. All right, the theory is completely gapped. The photon eats the phase of H to make a massive vector boson. The Higgs field, the radial mode of the Higgs field is also massive. So in the deep IR, this theory has no massless degree of freedom. However, because the gauge symmetry is broken to its ZQE subgroup, there is a ZQE topological discrete gauge theory living at long distances that I'll say a few things about in a second. The first thing to note is that the continuous U1 magnetic symmetry, which remember is exact in this model, it's the flux conservation symmetry of this superconductor, if you will, is unbroken. One way to see that is that the theory is gapped. There's no possible Goldstone boson for it. Very good. So what does it mean for this U1 symmetry to be unbroken? It means we should have objects that are charged under that symmetry, and that charge should be conserved. What are those objects? Well, the operators that were charged under U1 magnetic were the 't Hooft lines, right? What happens when you act with an 't Hooft line on the vacuum? It creates a magnetic vortex string. This model famously has Abrikosov-Nielsen-Olson vortex strings, which are magnetic vortices. Those are solitons of the model, finite energy configurations that carry magnetic flux. And if you act on the vacuum with a 't Hooft line of charge Qm, then you create an A and O string of vorticity or magnetic flux Qm. Very good. Now, all of these strings have finite tension. They're physical, nice, well-behaved strings. So they have tension, which depends on Q magnetic, some positive number. Very good. So what happens if we repeat the calculation of the monopole, anti-monopole static potential from yesterday? Remember that we got that by looking at the expectation value of a large 't Hooft loop. Well, if you look at the expectation value of a large 't Hooft loop, separated by t in time and r in space, right? Remember this was e to the minus t times v q magnetic bar as a function of r. Then when you add 't Hooft line on the vacuum here, this operator creates an A and O string of length L or length r. And because the string has tension, finite tension, that means that the energy of this string is the tension, which depends on qm in general, times r. So this is a famous formula. This is a linearly confining potential coming from a string with finite tension, but it's a linearly confining potential for magnetic charges. This is the famous statement that a Higgs phase, an ordinary phase, can be thought of as a confining phase for monopole. And another famous reinterpretation of this formula is that you can write it as e to the minus the tension of the string times the area of this square loop, which is just r times t. And so this is the famous area law, the confining area law coming from finite tension strings. And because this area term decays much more rapidly than the perimeter term, at infinity, the expectation values of the loop all go to 0, and that's in accordance with the statement that the U1 magnetic symmetry is unbroken in this phase. So unbroken U1 magnetic is a good characterization of a Higgs phase. Very good. Now, in fact, there are even more interesting vortices than the ones I've described here. The ones I've described here have integer vorticity. Because of the low energy ZQE gauge theory, there are actual fractional vortices as well. You can have vortices of fractional vorticity, rational vorticity, quantized in units of 1 over QE. The famous case that you may know about from superconductivity is the case when QE is 2, and then you can have half vortices, which are called pi fluxes. And those fractional vortices are not created by acting with genuine line operators on them. They are, because they're not properly quantized. They're, roughly speaking, fractionally quantized 't Hooft lines, which are not lines at all. They're lines surface attached. And the surface remembers that those vortices involve some polynomial of the low energy ZQ gauge fields. So we'll see a reflection of that very soon when I write down the low energy TQFT that describes this phase. Very good. Now, why do I mention these fractionalized vortices? Because I ended the last lecture by explaining that this model, or maybe I didn't end this way, but in any case, I mentioned that this model still has a mixed anomaly between the U1 magnetic symmetry and the ZQE electric symmetry. So these are the one-form symmetries on the model, and they still have a discrete mixed anomaly. However, I've just argued that the U1 magnetic symmetry is unbroken and the model is gapped, so we should be a little bit worried about how this anomaly is matched. And roughly speaking, it'll be matched because of these fractional vortices, or that's at least one way of thinking about it. All right. By contrast, this electric symmetry here is spontaneously broken. The Wilson lines still have perimeter law. One way to see that is that if you compute the static potential for two electric charges that are well separated, then because of Higgsing, the force between them is exponentially small. It's a short distance force. So V decays exponentially to a constant, and you get perimeter law. So this one is unbroken. Sorry, this one is broken. OK, so when we spontaneously broke a continuous one-form symmetry, we got a photon. That was the Goldstone boson. Here we have a discrete one-form symmetry that's supposed to be spontaneously broken. And the thing you can ask is sort of what does that give us? What's the analog of the Goldstone boson? And the analog of the Goldstone boson is the deconfined ZQ gauge theory at long distances. So let me write down a nice effective description for that gauge theory, and then I'll say a few things about it. So in the deep IR, one way, not the only way, to describe this ZQ gauge theory is as follows. You can write it as a BF theory with coefficient QE, where F is literally dA, the original Maxwell field. B is a new dynamical two-form gauge field, which was not present in the original model. You can, roughly speaking, think of B as being dual to the phase of the Higgs field H. The phase of the Higgs field H, which is the thing that gets eaten by the photon to gap the theory, is a compact boson. And in 4 dimensions, if you dualize a compact boson, you get a B field, not another boson. In 2 dimensions, you get another boson. In 4 dimensions, you get a B field. So this is, roughly speaking, the dual description of the phase of H. And therefore, this cross term, roughly speaking, captures the Higgsing that takes place. And these are all the dynamical fields in the theory. But it'll also be important for us to understand the background field. So, of course, the Maxwell field comes with its B electric background field. Remember that this B electric is now discrete. It's ZQ valued. And we still have the coupling to the continuous magnetic background field as well. All right. So this new B field, which is dynamical, has itself standard U1 two-form gauge transformations with 2π integer fluxes. By now, this should be like a broken record. OK. Now, I'm not going to derive this presentation, but roughly speaking, it's a small exercise for you to do it by taking the original Higgs model, throwing out the radial mode of the Higgs, just keeping the phase of chi, dualizing it just as I derived electric-magnetic duality yesterday, and then you'll land on this presentation. OK. So let's, for a moment, in your mind, imagine turning off the background fields, B electric and B magnetic, so that we only have this dynamical BF theory. The first thing I want to explain briefly is why this is a good description of ZQ gauge theory. Well, one way to see that is that you can think of little b as a Lagrange multiplier whose job in life it is to reduce little a to a flat ZQ gauge field. Right, the equation of motion for B sets F to 0, so A is flat, and then actually the flux sum over B sets the holonomies of A to be ZQ valued. So if you do the path integral over B first, that's the presentation you get. You can get a different presentation by thinking of this in reverse. Do the path integral over A. Then A is a Lagrange multiplier whose job in life it is to reduce B to a ZQ valued two-form gauge field. So this theory simultaneously describes ZQE one-form gauge theory and ZQE two-form gauge theory. This is a standard thing in duality. The gauge group is not a meaningful concept. Two theories based on different gauge groups can have exactly the same physics. The presentation we naturally land on from the Higgs model is as a ZQ ordinary gauge theory. But you can also think of it as a two-form gauge theory, which we'll make use of in about 5 minutes. All right. And the topological operators in this theory are the Wilson and the 't Hooft lines. But their charges are only in ZQE. Right. So we have Wilson lines of charge m, defined as always. And we have not Wilson lines, but Wilson surfaces for little b. These are the holonomies of b over some 2 cycle. Here I put, I guess, m. And here I put n. These are integers. And I'm not going to do the computation, but if you do the computation in this free Gaussian theory, which is a not completely trivial but straightforward thing, then you find the exponential, you write out in the second line, of 2 pi I mn over QE times the linking number of the curve with the surface. Right, we're in 4 dimensions. We've already discussed at great length how surfaces can link lines, how one-form symmetries act on lines. This 2-point function here is proportional to the linking. So it's only non-zero if the Wilson surface for B links the Wilson line for A. So this is basically a ZQ-valued phase that depends on the linking number and the charges of the holonomies here. And you see that everything is ZQ-valued. Now, you can see from this formula that this Wilson surface for B implements the discrete ZQE1 form symmetry. It is the symmetry defect that generates the ZQE1 form symmetry on the Wilson lines by linking. Right? This is what we said the symmetry defect does. Now, another thing to note, very straightforwardly, is that all of these topological operators have non-zero expectation values in the sense that we define them. So in other words, they obey the analog of perimeter law. And one way to see that is because if you take a single Wilson loop, for example, because it's topological, you can scale it up or down any way you want. You can shrink it down to a point, and then you just get a constant. You just get the identity. So this shows you why this ZQE symmetry is spontaneously broken in DIR by these loops. Okay. Now I would like to briefly explain how the mixed anomaly that we had before is matched by this DQFT in the infrared. So far, I've not said anything about the magnetic symmetry. I've only said that the Wilson surfaces for B generate the electric symmetry. Nevertheless, we know that we're supposed to get a mixed anomaly that corresponds to this 5D. Well, if I write it in terms of the original variables, it looks like that. And the only thing that's happened now is that this DE has been reduced modulo ZQ. So let me not try to write it in a different way. All right.
Did DA also generate a symmetry?
DA also generates a symmetry. That's a good question. DA generates a new emergent symmetry of this model, which is not present in the UV. A is the generator of the symmetry, and you see that it's codimension 3. So it generates a 2-form symmetry. Right? And the B surfaces are charged under that 2-form symmetry. Yeah, and it's actually that emergent 2-form symmetry that is responsible for matching the anomaly. I'll show that right now, although I may or may not say it in exactly those words. All right, so what I would like to explain now is the relationship between this term and the fractional charge of the vortices. Remember that in Maxwell theory, this term was responsible for the anomaly, right? If you shift F by d lambda electric, then this whole term shifts by the C number that was responsible for the anomaly. And this term just got inherited from Maxwell theory on the nose. So it's still this term that's responsible for matching the anomaly. And the thing I want to very briefly explain is that the meaning of this term in the low energy TQFT is that the fractional vortices of the low energy gauge theory also carry fractional magnetic 1-form flux or charge. Now, those fractional vortices are precisely generated by the Wilson surfaces of little b. Right, once we get to the deep IR, all the vortices have finite tension. They're very massive. Once we get to this IR TQFT, they're long gone. The only thing that has remained is their effect on the low energy gauge fields. And the statement is that a charge n vortex introduces a non-trivial twist in the holonomy of the U1 gauge field in the transverse direction, which is what this formula tells you. So this operator can be thought of as creating a fractionally charged vortex. Now, do I want to? Yeah, maybe I'll write this one line just because it's an important point. So imagine you insert this operator into the path integral. And then you integrate out the field F. Then you see that this term acts as a source for F. And you find that F is 2 pi over n Q electric plus the Poincare dual of sigma 2. Where this Poincare dual of sigma 2 really means a delta function representative of this Poincare dual 2 cycle to sigma 2. I think we saw that in Greg's lecture yesterday. Okay, so if we plug this formula back into the path integral for F, sorry that they are on opposing ends of the room, then because of this BF term here, right, I'm going to get a term that looks like the integral of B magnetic wedge F. That's the BF term. Right? This is SBF. And when I plug in this solution for F in the presence of a vortex created by the B surface, then I get, what do I get? So F lives on the Poincare dual cycle to sigma, and that means I'm actually going to get a term involving the B field integrated over sigma with coefficient In over QE. I'm going to raise the blackboard in a second so you guys can see. So you see that the BF term in the presence of this fractional vortex creates on the world sheet of the vortex, which is sigma 2, an insertion of the non-magnetic B field, coefficient N charge with the U1 magnetic symmetry. This is a kind of 4-dimensional grade phenomenon you might be familiar with in 3 dimensions. For example, in the fractional quantum Hall effect, the electron has fractional electric charge. And the way in which this comes about is entirely analogous to the derivation I did here, just in one lower dimension. Okay. And because this BF term is responsible for matching the anomaly, you see that the relationship between the fraction and the anomaly. So this is the first example of this kind. We'll see other examples. Yeah.
Who got the fractional charge? Why not?
No, the surface defect B, the Wilson surface for B, which represents the world sheet of a probe vortex in the low energy TQFT. Yeah, there was a question there. Which equation? This one? That's the equation. So this, I'm inserting this operator into the action, and then I'm solving for F. This is the equation of motion for F in the presence of such an insertion. Right, there's an F wedge little b term, and now there's a b term as a source. Sorry, it's not the F equation of motion. It's the B equation of motion. I apologize. It's the B equation of motion. which sets F proportional to a source. Yeah, there's a BE, but that doesn't matter for what I'm doing. So you're right. I wrote it imprecisely. The correct statement is that there's also a BE, I think with a minus sign, but that has no effect on what I'm saying. So this is the B2 equation of motion. Sorry about that, I misspoke. Okay, very good. And now I'm going to have to make a crucial about what to skip and what to cover. I think in view of time, I'm going to skip the discussion I had intended about gauging subgroups of the electric and the magnetic symmetry. So now that we have encountered a description of this ZQ gauge theory, and we understood that it could be thought of as either ZQ gauge theory for an ordinary one-form gauge field or ZQ gauge theory for a two-form gauge field, we can use this gadget to start gauging discrete subgroups of either U1 electric or U1 magnetic. And that's a fun thing to do. Remember, those were anomaly-free subgroups. And you can do that very explicitly because I showed you how to couple the action to background fields. And then in order to gauge a discrete subgroup of either B electric or B magnetic, you just make some of those background fields dynamical. In the case of B magnetic, you also have to embed the discrete gauge fields into the continuous ones. And then you add this BF action and path integral. And this is a fun exercise because what you'll see is that when you gauge a subgroup, a ZN subgroup of the U1 magnetic, you'll land on the same model, except that two things will change. First of all, the electric coupling, E, will be multiplied by a factor of n. And secondly, the charge of the field H will be multiplied by a factor of n. So by gauging a ZN subgroup of the U1 magnetic symmetry, you can relate models with different Q, with different electric charge. Conversely, if you gauge a subgroup of the electric symmetry, so if n is a divisor of Q electric, and you gauge a Zn subgroup of the electric symmetry, then you reduce the charge of the Higgs field by that factor n. So these are inverse operations. You can gauge a discrete subgroup of U1 magnetic, you can gauge a discrete subgroup of U1 electric, and you can go back and forth between models that have different electric charge. So these models are very simply related by discrete gauging. And discrete gauging is a very nice operation because it commutes with all non-trivial dynamics. It's kind of a rigid operation. You can do it in the UV, you can do it in the IR. And if I had more time, I would elaborate on that. But in the interest of time, I'd like to move on to another topic. If somebody's interested, I'm happy to kind of explain it more about it offline. All right. Okay, so I would like to say a few more things. Everything we've said here has been in a model with a Higgs field of electric charge Q and no magnetic charge. We can use electric magnetic duality, which basically just flips the labels E and M, to relate this whole discussion to a model where we have a U1 gauge field coupled to a magnetically charged Higgs field, but no electric charge. Then the entire story is the same. All the phases are the same. The physics is the same. The only thing that changes are the words. So you switch the labels electric and magnetic, and then you repeat the analysis. And for positive masses, you are back in the and these symmetries are spontaneously broken. And in the Higgs phase, you encounter a situation where the following happens. Let me switch the labels and say the correct words. So if you do S duality, then you have a system with a magnetic charge, a magnetic Higgs field, H. And the symmetries are now U1 electric times ZQ magnetic. And in the Higgs phase of this model, when the H field condenses, this is spontaneously broken, but the electric symmetry is unbroken. And that means that electric charges are linearly confined by finite tension strings. Yeah. No, I'm saying if you act with S duality on the abelian Higgs model, you get to a model in which H has magnetic charge. And you just exchange the word electric and magnetic everywhere. So in the Higgs phase, in this magnetic Higgs phase, U1 electric is unbroken. And that means that all the operators that are charged under it, which are the Wilson loops, the electrically charged loops, all have area law. They all have zero expectation value. And therefore, electric charges are linearly confined by strings of this tension, and the U1 electric symmetry is unbroken. So the magnetic Higgs phase, physically, in terms of symmetries, in terms of everything, is tantamount to electric confinement. And so confinement and Higgsing are electric-magnetic duals. This was a famous insight of Mandelstam and 't Hooft, and it plays a role in our kind of modern understanding of confinement, even in non-abelian theories. And the reason for that is that this abelian Higgs model, suitably interpreted, often appears in an interesting effective description of those theories. So now, if the theory happens to have both electric and magnetic charges, then the symmetries are even smaller. Then the U1 magnetic symmetry here is also broken. The U1 electric symmetry is also broken. And the most extreme case of that is if you have an electric charge 1 and a magnetic charge 1 field. So all the electric and magnetic charges are actually present. Then you have no one-form symmetry whatsoever. Right? And in that situation, there is no more symmetry-based principle for characterizing Higgsing and confining and Coulomb phases, right? At least at the level of sophistication that we've talked about. And if you believe that all phases should somehow be characterized by symmetries, then this might lead you to speculate that in a model that has all electric charges and all magnetic charges, so in other words, no one-form symmetries whatsoever, there is actually no invariant distinction between Higgs and confining phases. And this is a famous fact that was shown explicitly in certain lattice models, for example, by Fatkin and Schenker and other people. And it goes under the general slogan of Higgs confinement continuity in theories with no one-form symmetries. So for example, QCD with fundamentals, like real QCD, doesn't have a one-form symmetry, and it's believed to have this property. So when people talk about understanding confinement or proving confinement in QCD, for what they actually mean. Any questions about this? Yeah.
What happens when the E in the original Lagrangian is like square root of 2 pi, where we have like the asymmetry, S-duality?
Not anymore, because this model, that was what I was saying before too. This model no longer enjoys any self-duality at a special value of E. That's the only place this could happen is when you have both an electric charge 1 field and a magnetic charge 1 field. And then S-duality could exchange them. And in fact, people have studied such systems. There's nice work on lattice theories that have exact S-duality with an electric and a magnetic field on the lattice. Yep. And there's an interesting phase diagram, and you can study that.
And also very basic, like when you say equals to 1, is in relation to the E charge, right? The Maxwell Lagrangian.
What did I say?
These charges, they are all measured in
They're integers. We're working in units in which the charges are integers.
Yeah, but what gives there is like the initial charge in the Maxwell Lagrangian, right?
Well, I'm not quite sure what you're asking. Maybe what you're asking is that often in elementary presentations, we rescale the Maxwell field in such a way that the coefficient of the kinetic term is 1. And then the charge in the covariant derivative will not be an integer, it'll be e times an integer. Is that what you're asking? Yeah. That's fine. You can do that, of course. But from the beginning, I've only ever worked in the convention in which the charges are integers. All right, other questions? Yeah.
Is there any sense in the story that you told for the last 2 days that the pure gauge theory itself has a confining phase?
Well, you mean pure Maxwell theory?
Yeah.
So in the continuum, the answer is no. So it starts with this continuum Lagrangian. It's free field theory. There's no doubt that it's in the Coulomb phase. But maybe what you're asking about is what happens when you put the theory on the lattice.
I know completely what's happening then. I'm translating in my head, and then there are places where your words don't map on the things that I know about.
Maybe I can say 2 words about that because it is actually a very nice comment that I wanted to make. So since you asked about it, I'll make it. When you, so this is not an answer to you because you know all this. I'm saying it for everyone. When you put U1 gauge theory, in other words, quote unquote, pure Maxwell theory on the lattice in the standard Wilson way, then you actually do not preserve both the U1 electric and the U1 magnetic. The U1 electric symmetry is preserved, so you don't have electric charges, but the U1 magnetic is explicitly broken because there's no Bianchi identity on the lattice. And that means that the theory on the lattice is actually not pure Maxwell theory, it's pure Maxwell theory to dynamical monopoles. The best continuum toy model to have in mind for this theory is exactly this. A magnetic Higgs model with a charge 1 magnetic Higgs field. And if you dial the lattice coupling, which is a dimensionless coupling, from strong to weak, at very strong coupling, you get even in the U1 lattice theory. That's the famous strong coupling limit of lattice gauge theories, which is always confining. And at weak coupling, you get the Coulomb phase. You get the free Maxwell field. And at intermediate values of the coupling, you get an interesting transition. And it's believed, I hope you can confirm this, it's believed that this transition is first order. Nobody knows. But I would say so I don't know what the best interpretation of the data is, but if you take this cartoon model in your head of a charge 1 Higgs field, then the Coleman-Weinberg effect would suggest that the transition should be first order. Right. So maybe it's not a settled question, and that's even better. Then somebody should settle it. Yeah, I know. It's much harder to understand phase transitions than phases. And phases are hard enough. Any other questions? So thanks for the question. Any other questions before we move on to the sort of last topic of the day? Okay, so the last topic of the day is a further enrichment of this model. So you see, right now we've had an interesting discussion about a model that had charged matter and one-form symmetries, and it did interesting things with those one-form symmetries. But I haven't talked a lot about zero-form symmetries, and that's because this model didn't have a whole bunch of them. It had a few discrete ones, but they weren't so important in what I said. What I would like to do now is to generalize this theory dramatically by upgrading from 1 Higgs field to 2 Higgs fields. So Hi is a pair of Higgs field. I is a flavor index. So this is what you might call NF equals to 2 scalar QED. And otherwise, the Lagrangian is exactly the same. Maybe I shouldn't have erased it. Well, since I'm writing it schematically, it's not so hard to put it back. And I'm assuming here that these have electric charge 1. So I'm no longer discussing the more general case of arbitrary electric charge. So this system does not have a one-form symmetry. The U1 electric one-form symmetry in Maxwell theory is gone, but the Bianchi identity still holds, and we have the U1 magnetic. Very good. Now, when you first encounter this model in QFT class, and you're asked the question, what is the global symmetry of this model? Well, we can take a poll here, but this is no longer an unbiased sample. You've been biased already with fancy ideas. I bet you that the 0th order answer would have been that the global symmetry of this model is SU2. This model has an SU2 flavor symmetry under which the doublet transforms in the fundamental representation. So this is an SU2 matrix. And I'm assuming here that the potential is chosen in such a way that this is also the a symmetry of the potential. And so tentatively, you would have said that the symmetries of this model are that it has a U1 gauge symmetry and an SU2 flavor symmetry, and that's it. Well, don't spoil my. I'll get to U2 in a second. Of course. Just remember, this H is actually the same as the Higgs field in the standard model. So people normally say that the gauge group of the standard model is U1 times SU2, not U2. Okay. Very good. So the U2 that Greg is talking about, and which he's of course correct about, comes about because one element of SU2, which is the central element, -1, which is minus the identity matrix, is actually just acts as -1 on the Higgs field. And that can be undone by a gauge transformation with angle pi, because H also has charge 1 under the U1 gauge group. Okay? So this element of SU2 flavor is actually gauged, and therefore the quotient of SU2F by this gauge Z2 is SO3. So the true flavor symmetry of this model is SO3. This is also the symmetry that acts on all gauge invariant local operators. Whenever you make gauge invariant local operators, maybe something like H bar H with some I and J indices, you can see that these always transforms as tensors under SO3. You cannot make a gauge invariant local operator that's a spinner of SO3. Very good. Now, this is something that you've not heard about for the first time today. In last week's lecture, Nadi discussed the symmetries of the two-state model, the two-state system. So two-state Hilbert space with sigma matrices acting on it as operators. And there, too, the superficial SU2 or U2 symmetry of the model got reduced to SO3 because the phases there didn't matter. So this is a very similar phenomenon, except that here the phases don't matter, not because of the projectiveness of quantum mechanics exactly, but right now at least because of the gauge symmetry. Very good. So you also learned that in that system, the Hilbert is in fact in a projective representation of that SO3 because it's a two-state system. It cannot be in a triplet or whatever. So it has to be acted on by the SU2, and therefore the entire Hilbert space is in a projective representation of the symmetry group. And so if you take that analogy seriously, and you should, then you might ask, in this model, is there any interesting consequence of the fact that the symmetry is SO3, but there is actually a field H which transforms in the doublet representation, which transforms projectively? And, well, the obvious answer to what transforms projectively is H. That's not a good answer because H is invariant. But you can make something gauge invariant that transforms projectively. You can take a Wilson line of charge 1, and you can end it on H. This ending is precisely what was responsible for the breaking of the one-form symmetry. But now we have a gauge invariant local, semi-local operator, right? A line ending on a point that transforms projectively under SO3 because I is an SU2 doublet index. So there's something interesting and projective about this model. And this projectiveness will actually sort of partially make up for the fact that this model doesn't have a one-form symmetry. The projectiveness of the SO3 gives us a new handle that will play a very similar type of role. So in order to see that, let's play the same game we played before with the abelian Higgs model with a single Higgs field. Let's go to the Coulomb phase and then the Higgs phase and see what happens. So let's add a positive mass for the Higgs field so that we can integrate it out. then in the deep IR, we just have Maxwell theory again, and Maxwell theory will have its emergent U1 electric one-form symmetry, and of course also the exact U1 magnetic, under which the low energy Wilson and 't Hooft lines are charged. And remember that if you take a Wilson line of charge 1 in Maxwell theory, that represents a heavy probe particle of electric charge 1. Right. Very good. Now, in this model, we don't just know that H had electric charge 1. We also know that it transforms as a doublet under SU2, and in particular, projectively under SO3. Is there any way we can impart this information onto the Wilson line? Can we somehow tell the Wilson line that H had that property? Well, let's think about how we might do that. So one way we can do that is to turn on background fields for the SO3 or the SU2 flavor symmetry. Background gauge fields. These are no ordinary one-form background Yang-Mills fields. They're non-dynamical, but they're standard Yang-Mills fields. Let's, for the moment, pretend like the symmetry is SU2, and then we'll say how to take into account the sophistication that it's actually SO. Well, if we really have SU2F background gauge fields, let me call them big A, valued in the Lie algebra of SU2, then one way you might think of encoding the statement that the Wilson line has some charge under this SU2 symmetry is to superimpose on it a Wilson line for the background gauge field. So you can add on top of this a Wilson line in the representation R of the SU2 flavor gauge field, right? So you can write this in the usual way, as the trace in the representation R of the path-ordered exponential of, e to the I integral of A. In other words, the holonomy of the Mills field, where the path ordering comes about because of the non-abelianness. And this would be the background Wilson line for the SU2 flavor gauge field. It would also be localized on this line. Very good. So this is just a non-abelian Wilson line in this representation. And this sounds like a good way of describing what representation the line is in. So maybe we just take R to be the doublet representation, fundamental of SU2. Great. So we have apparently succeeded in making the Wilson line a doublet of SU2, but we've also failed spectacularly in an important way. And the way in which we have failed is we have done this by adding a local counterterm in the background fields to the line. And this local counterterm, you should think of it as being exactly on the same footing as the perimeter counterterm we discussed yesterday, which is a scheme-dependent thing that different observers might or might not add, and therefore doesn't capture anything universal about the theory, doesn't capture any real information. Quite the contrary, it encodes an ambiguity. It encodes the ambiguity that a low-energy observer, who is able to add these background Wilson lines on top of the dynamical one, doesn't know what representation of SU2 the line is actually in. So this line doesn't encode information, it encodes ignorance, as counterterms always do, right? And if the flavor symmetry is really SU2, that's it. This is all you can do. So in fact, what you learn is that if the flavor symmetry is SU2, you're completely ignorant about the representation of the line. And one way of thinking about this is that the case of SU2 flavor symmetry corresponds to having a completely electrically neutral doublet of SU2 in the theory, maybe some heavy extra field that I didn't write. And that could then add this background Wilson line in any representation. Very good. But we had a more special situation, right? We did not have an electrically neutral field that was a doublet of SU2. We had a charge 1 field that was a doublet of SU2. Right? And that's what reduced the flavor symmetry from SU2 to SO3. So somehow we need to figure out how to upgrade this discussion to SO3. And so what we clearly need to do, first of all, is to take the background fields A to be SO3 background fields, not SU2 background fields. That's the statement that the model actually has SO3 symmetry. You can call SO3 bundles and connections on them. All right. Now, if you play the same game with the local counterterms in terms of SO3 representations, then you see that the only things that genuinely line genuine representations of SO3. So only the Wilson lines in SO3 representations are counterterms. That means that the information that is ambiguous and that's encoded by the counterterm is the integer part of the spin of the representation. That's the SO3-ness of the representation, right? That's the integer spin representation. The spin under SO3 is not representable by a local SO3 Wilson line counterterm. And that somehow means that the intrinsic statement that the line is projective under SO3 is meaningful, cannot be screwed around with by adding counterterms, even though we can't say precisely what representation it is. These counterterms tell you that you can't say whether it's spin a half, or it's spin 3 halves, or it's spin 5 halves, but you can say that it's definitely projective. This is analogous to the statement that the whole Hilbert space of the two-spade system is projective in SO3. All right. So now the question we need to solve, we're back to square one. So we now know that we can only use integer counterterms, but we still haven't figured out how to impart the information to the line that it's actually projective under SO3. And in order to do that, we need to use a gadget that is available because SO3 is topologically distinct. And the statement is that every SU2 bundle can also be thought of as an SO3 bundle, but not the other way around. There are some SO3 bundles that cannot be lifted to SU2 bundles. And the obstruction to lifting an SU2 bundle to SO3 is the second Stiefel-Whitney class of the SO3 bundle, which is a characteristic cohomology class valued in H2 with coefficients in Z2.
Is that the other way?
I'm sorry, this is the central point. Yes, you're absolutely right. Very good. So this is a Z2 valued gadget, which is in H2 with coefficients of Z2. What does that remind you of? What did we see that lived in H2 with coefficient in ZQ? Anyone? A Z2 gauge field, yeah, but what kind of gauge field? What form degree? A what? Yeah, but what form degree? Two form, a B field. So this W2 of SO3 is going to play a little bit a role analogous to a B field, even though we do not have a one-form symmetry in this model. And one way this comes about is the way that we encode the projectiveness of the line. The way we encode the projectiveness of the line is we take here the Wilson line of 1. This is the curve C. We attach an open surface whose boundary is C. And then we declare that in the presence of an SO3 background gauge field, this surface has attached on it the integral of this W2 of SO3 over the surface sigma 2. Sorry, there should be a pi here. Why is there a pi? Because W2 is valued in Z2 cohomology, and I need this pi to convert this into a sign. This is
Sigma 2 is a chain, not a sign. So we need to lift W2 to a 2 chain.
sorry?
Sigma 2 is a chain, not a sign.
I will come to that in a second. So very good. So Greg is already anticipating the inconsistency in this formula. this formula is not sensible if sigma 2 has a boundary. It's sensible if sigma 2 is closed. Then this is a completely meaningful formula. It makes sense to evaluate a Z2 cohomology class on a closed Z2 cycle. Then you get a well-defined sign. Okay? However, on two cycles with boundary, this is not sensible. And I think what you are starting to get towards is the state that if you actually want to make sense of this on an open cycle, then you need to pick a trivialization of W2 near the boundary. And this choice of trivialization on the boundary is actually the thing that encodes the information about the boundary Hilbert space being in a projective SO3 representation. This is, if you wish, this is the correct non-local way to write the half-integer spin-Wilson line in SO3. Right? In SO3, you cannot write the half-integer spin-Wilson line as a local line counter term, but you can write it as a surface counter, as a surface term. I shouldn't call it a counter term because it's not local on the line. Okay? So this thing doesn't modify the line by a counter term. It captures some interesting information about the line. And in fact, the way you should think about this surface is an anomaly inflow in quantum mechanics. Forget for a second about the fact that the line lives in 4 dimensions. Just think of the line as a 1D quantum mechanical system that has SO3 symmetry and that is projective. This was one of the first examples you saw of an anomaly in this school. If you remember that we typically like all anomalies that we encounter to be captured by some kind of inflow action, some kind of SPT that encodes the anomaly, this is the 2-dimensional SPT for SO3 symmetry that encodes this projectiveness anomaly in quantum mechanics. Now, so this is a statement about quantum mechanics, but now we would like to uplift the discussion to Maxwell theory, which lives in a 4-dimensional space. So now these lines live in 4-dimensional space-time. So how do we implement this attachment of the surface W2 to the line? Well, this is where the analogy with B electric comes in handy, right? So I already told you that just by virtue of its being a cohomology class, it's tempting to think of this as an analog of B electric. I'm going to make this analogy even sharper by showing that if you plug in B electric equals pi times W2, we should think of this whole thing as being valid in Z2 cohomology, then the way that B electric couples to Maxwell theory automatically implements this attachment. Okay, let's see how this happens. Well, remember that in Maxwell theory, B electric coupled to I times B electric background couples to star of the electric current. This is basically star F up to factors. And this is the thing which when you integrate it over a small surface linking the Wilson line, spits out the charge of the Wilson line. So if you have a Wilson line of charge 1, right, then the integral over this small S2 linking the line is 1. And what you're left with is exactly, so this thing collapses to the integral of I B electric over the open surface sigma 2. That's Poincaré dual to this sphere. We already saw that earlier. Except that here, now it's B. It's the integral of B electric that lives on this surface. And what we want is I pi W2 of SO3. So if you make this substitution into the background fields of Maxwell theory, then you get the right attachment. So what you learned is that in order to capture the projectiveness of the Wilson lines under the SO3 flavor symmetry, you need to enrich Maxwell theory. Symmetry didn't have. You need to enrich it by the SO3 flavor symmetry, which was a zero-form symmetry. Maxwell theory, it doesn't have interesting zero-form symmetries like SO3, but it does have one-form symmetries, be electric, be magnetic. And via the embedding of the zero-form symmetry into the one-form background gauge fields, you can give the lines of the theory, in this case it was the Wilson lines, fractional charges or projective representations under the zero-form symmetry. So this is something known as symmetry fractionalization. It's a very general phenomenon, happens all over the place. And a precise statement is that the line operators of some theory, could be a gauge theory, could be a TQFT, transform projectively. It's not just restricted to lines, it could be any defect. Okay, so there's two things I want to mention. Then if I have time at the end, I'll discuss the Higgs phase of this model. If not, we'll do it tomorrow because it's appropriate in the discussion tomorrow. Now, the first point is that, remember that I told you that coupling Maxwell theory to flat B fields can be reinterpreted in terms of twisted gauge fields. And here's an example where we are instructed to couple Maxwell theory to a flat B field. So if you use the prescription that we had before, right, the thing that we called the twisted gauge field C had field strength, which was equal to F minus B electric, and it had a flux, which was in 2 pi z plus pi times the integral of B electric over sigma. Now, we are working in a special case of this, where B electric is pi times W2 of SO3. Sorry, there's no pi here yet. The pi comes when we plug in W2. Very good. Now, this type of twisted gauge field, which I think Greg was anticipating a while ago, has a very natural description in terms of U2 symmetry, U2 gauge fields. What we are actually doing is we're describing a system that has a U2 symmetry. U2 as a group is U1 times SU2 with a common Z2 that's shared. In our example, the U1 is gauged, and the SU2 is a flavor symmetry. If you get rid of the gauge symmetry, you mod out by the gauge symmetry, then you get SU2F mod Z2, which gives you the SO3 flavor symmetry. But if you keep track of both, you see that their fluxes are actually linked. And so one way of saying what this model has is it has a U2 symmetry. Some of it is gauged, and some of it is global. But the fact that it's U2 means that the U2 gauge fields automatically satisfy this twisted condition. In other words, if C is the U1 inside SU2, it automatically has this twisted flux condition. This is another way we could have said the whole thing from the get-go. The more physicsy way of saying what's going on here is that in a general SO3 background, an SU2 doublet, a projective representation like HI, is not well defined. There'll be kind of minor ambiguities that go around various cycles. And those ambiguities are precisely associated with those cycles where W2 of the SO3 bundle is non-trivial. But because H also has electric charge 1, you can make the rule that on every cycle where there is an SO3 problem, you insist that the U1 gauge field has fractional magnetic flux, fractional monopole flux. And you pick the fraction to be a half, and that gives you kind of compensating minus signs. And this twisted condition is exactly what you need so that the minus sign ambiguities in the SO3 part and in the U1 part cancel. So that HI is a well-defined section of U2, which it is.
Thomas, we've got 10 minutes.
Thanks. Now, for people who've seen spin C structures before, this should ring many bells. I didn't want to get into that discussion, but you can do exactly the same thing with spin instead of with a global SO3 symmetry. For example, if you take QED with electrons of charge 1, then they are spin a half. And normally you think that you need a spin structure to study that theory on curved manifolds, but in fact you can do it even without a spin structure as long as you twist the dynamical U1 gauge field in a way that's completely analogous to this, except that the W2 of the SO3 bundle will be replaced by W2 of the tangent bundle of the manifold. So I don't want to dwell on that, but I just wanted to mention that for people who might have heard about this. All right. And the last comment I want to make about this phase is about the anomaly. So remember, maybe it's still even up on the board, maybe not. Remember that Maxwell theory had the famous anomaly that we kept harping on. B electric times dB magnetic anomaly. Now, this theory doesn't have an electric one-form symmetry. It has an emergent one in the IR, but the microscopic model does not have an exact B electric symmetry. It does have the B magnetic. However, so B electric is not a good one-form background gauge field. However, we have learned that the coupling to the SO3 flavor symmetry and the projectiveness of the Wilson lines are tantamount to setting B electric to be pi times W2 of the SO3 bundle. So let's do that in this formula. Let's replace this by pi times W2 of the SO3 bundle, and then we can pull out the 2 pi here and reduce this integer cohomology class mod 2. This is W2 of the SO3 flavor bundle. So this anomaly is non-trivial. It's a Z2 valued anomaly. W2 is a Z2 valued background field. But it's non-trivial. And it's non-trivial even though we are in a model that doesn't have an electric one-form symmetry. The W2 of the SO3 bundle, as I kind of alluded to, plays the role that an electric one-form gauge field might have played. And it means that this model with the SO3 symmetry can never be made gapped and trivial. Okay? Here we made it go to a Coulomb phase, so it's definitely gapless. But what this tells you is that anything you do to this model, any potential you add, any other fields you add, as long as they respect the SO3 symmetry and the kind of twisted condition, the statement that projective representations of SO3 have odd charges and non-projective ones have even charges, this anomaly will always be non-trivial. You'll never be able to gap the model. All right, any questions about this? So I have 6-7 minutes left. Let me actually start our discussion of what happens if you try to drive this model to a Higgs phase. One way you might imagine gapping this model is by driving it to a Higgs phase. In the case of charge 1, that was how we managed to do it. Well, what happens if we take this model and we take the mass squared to be very negative, right, in this potential, then the scalar h gets a vacuum expectation value. So if m squared is negative, we're in the Higgs phase. H gets a VEV. And now we have to understand what this means. The fact that H gets a VEV definitely means that some components of H will be eaten by the gauge field, which will become massive. But this anomaly tells you that for sure, no matter what happens, we cannot end up with the trivial theory. And that's despite the fact that we have a model where the electric charge is 1, right? Remember that in the abelian Higgs model with charge 1 and no SO3 symmetry, the Higgs phase was completely trivial. It was gapped, trivial, and there was no anomaly, right? In this model, that's not true. We have a Higgs field of electric charge 1, but the anomaly is still not trivial. And it's easy to see that the low energy theory in this case is not just non-trivial, it's actually gapless. And the reason it's gapless is because this non-zero expectation value for H doesn't just Higgs the U1 gauge symmetry, so U1 gauge is Higgsed to nothing. I is an SU2 doublet index, and that means the SU2 or SO3 flavor symmetry is also spontaneously broken. How do you see that? Well, and what is it broken to? To analyze that, let's use an SU2 or an SO3 rotation to put H in a simple form. Let's pick a form where the value of H is just V0. You can always do that since H is a doublet. Okay? Now, in this presentation, there are two interesting U1s that act on H. There's the U1 gauge symmetry, which acts on V by phases. And there's the Cartan of the SU2 flavor symmetry, which acts on H like the Cartan does. But because the second component of H is 0, it also just acts on V by phases. So that means you can find the diagonal subgroup that mixes the Cartan of the SU2 symmetry with the U1 gauge symmetry that actually leads to an unbroken U1 global symmetry. So there's an unbroken U1, which is the Cartan of the SO3 flavor symmetry, with the extra small caveat that you have to admix into it as, the gauge symmetry as well. That's always allowed. You're always allowed to take a global symmetry and admix into it a bit of gauge symmetry. The converse is not true. Okay. This kind of breaking pattern where you have a global and a gauge symmetry and they break to the diagonal is also called sometimes, well, in QCD, it's called color flavor locking. In here, so it's gauge flavor locking. And it has interesting consequences. For example, it's what describes very high density QCD, which is roughly speaking described by a similar type of Higgs model. Okay. So the SO3 symmetry is broken to its U1 Cartan. And what does that mean? Well, Goldstone's theorem tells us that for every broken generator of SO3, we get a massless Goldstone boson. So this theory actually is gapless. And it has two massless Goldstone bosons. What do they live in? What coset space do they live in? They live in SO3 modulo U1, which is CP1. So the low energy theory is the CP1 model in 4 dimensions. This is also a model that you've seen before at this school from various points of view. Here it arises as the target space of these Goldstone bosons in our 4D theory. And the fact that the symmetry is spontaneously broken like this and that you have massless Goldstones is what manages to match the anomaly. But in order to explain that, and I'm not going to be able to do it now, I need to explain a little bit more about how the magnetic symmetry even acts in the CP1 model. So I'm going to do that tomorrow. And then we're going to graduate to non-abelian examples where these kind of abelian models that we've been discussing appear as interesting, effective descriptions at low energy. Yeah.
What's the anomaly for general flavor? Like the F equals to some general number.
Well, if you have an arbitrary number of flavors, then naively the flavor symmetry is SUNF, and the correct global form is PSUNF. In other words, SUNF modulo its center. And PSUNF also has a W2 class, which is valued in H2 with coefficients in ZNF. So this gets upgraded to a ZNF valued anomaly.
But for the odd number of the F, can you add some load cancel the anomaly?
Sorry?
I mean, there are some conditions for the.
Yeah, there are some conditions on NF. This doesn't always work, indeed. So you need to work it out. I think there's an even odd condition because you need to figure out how the center of the gauge group, sorry, how the center of SUNF interplays with the gauge group. So, but the recipe is always the same. So this is a big example. This is a small generalization. If you take any gauge theory with any flavor symmetry, you should correctly analyze the global form of the gauge and the global symmetries. In other words, you should be mindful of all these identifications. And then you learn what the actual background fields for your symmetry are and what the various cohomology classes are that describe them. And those give you interesting background fields that can appear in the action, in the partition function, as anomalies, as counterterms. So it enriches the number of things you can do beyond the situation where you just have the SU symmetry. Yeah. Other questions?
Now let's thank Thomas for his great work. And just a reminder, we do have a lecture at 2, but then that's the last lecture of the day. So Greg will speak at 2, and then we'll be done for the day.